Hello, welcome back. My name is Salma, and in this video I'm going to go over gates and circuits. Here's what I'm covering in details in this video. I'm also going to put timestamps in the caption, so feel free to skip to the subject you are struggling with. So first I'm going to go over what ones and zeros are. Next I'll explain truth tables and symbols. And for this video I'm using 6 gates, which are AND, OR, NOT, NAND, NOR, and exclusive OR. Next, I'll explain what circuits are, and finally, I'm going to show you what gates and circuits look like in real life. Before we get started with gates and truth tables, I really want to go over what ones and zeros are. If you're studying or dealing with anything that has to do with computer science, computer engineering, or electrical engineering, you've probably heard of ones and zeros before. But some people graduate without knowing how computers and devices in general understand ones and zeros. And I feel like this is a really good chance for you to understand what they are before we get started with gates. So I want you to think of ones and zeros as symbols. For example, something that we all do every day is switching the lights on and off. So if we use this example and having the switch as our variable, 1 here symbolizes switching on the lights and 0 symbolizes switching off the lights. So try to pause this video and think of what other examples could follow this example I just gave you. Okay, I have some examples here to what 1 or 0 can be a symbol of. So from the last example, 1 or 0 symbolizes the state of a variable. The thing that is worth mentioning here is that the value of this variable has to be of only 2 possibilities, meaning that it's a digital variable. So for example, if you are solving a true or false question, 1 symbolizes to true, 0 symbolizes to false, and so on. So yes or no, on and off, accept and decline, etc. Let's see a real life example here for what we just talked about. So if I'm saying that ones and zeros are symbols, how does the computer understand binary? Binary, by the way, is the representation in the base of 2. As we can see here, 75 in binary is this number that we have here. So I'm not going to go over what decimal to binary conversion is. So if you don't have knowledge in this subject, I would encourage you to pause this video and watch another video about decimal to binary conversion and then come back. So let's say you already know how to convert decimal to binary, and you got this binary number corresponding to 75. You can think of it as this. For each value I have here 1, 2, 4, which by the way are the powers of 2. So 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 3 is 8, and so on. So you can think of it as ones and zeros here as present and not present. So 1 symbolizes present and 0 symbolizes not present. When I'm trying to convert the binary back to decimal, I will come to the position 1 here, which is 2 to the power 0, and I want to see if it's present or not. So I'm going to check if the value that is in this position is 0 or 1. If it's 1, then it's present. If it's 0, then it's not. And here it happens to be present. So what I want to do is add 1 to all the numbers that are present and then move to the next position. So I'm going to add 1 and then move to the 2. If it's present, I'm going to add it as well. And then move to 4, which is to the power 2. If it's there, I'm going to add it. If it's not there, I'm not going to add it. And then 8 and 16 and so on. So let's put here, so we did find 1 because there was a 1 in the position, not a 0. And then we found 2. We didn't find 4, so we're not going to add it. We found 8, but we didn't find 16 nor 32. And we found 64. So if we add all these numbers, they should give us 75, which is our original number. So that's basically how we see ones and zeros as symbols in a binary number. So from this idea, let's move to a bigger example, which is how information gets sent over wire. Do information get sent over wire? Yes, that's basically how everything around us work. Well, not everything, but most of the things. If we look at this signal or square wave, given that 0 symbolizes 0 volts and 1 symbolizes 5 volts, send the number 75 over a wire. So that's what this example does. It simply send 75 over a wire. Of course, the time intervals and synchronization is a very important aspect, but I'm not going to talk about this, at least in this video. So that's how you send the number 75 over a wire. You convert it to binary, and then you send 0 volts corresponding to 0, and then 5 volts corresponding to 1. And then you keep doing it. You send 0 volts corresponding to 0 and 1 and 5 volts corresponding to the 1. That's how 75 is sent over a wire. And as you can see, it's very important that you know ones and zeros are nothing but symbols. So they here were symbols for 0 and 5 volts, and in other cases they will be symbols for something else. Okay, great. So that's how computers and devices understand numbers. What about characters and strings and things that we use in texting and posting on social media? That's a really important question. There's something called ASCII Table, which stands for American Standard Code for Information Interchange. And what it basically does is that it maps decimal and other type of texts like octal and hexadecimal to characters. So for example, the number that we have been working on, which is 75, corresponds to the character K. And that's how your computer understands this character and all the other characters corresponding to other numbers. So that's basically what I had for ones and zeros. I wanted to go over them because it's going to help you understand not just this video, but more general things in the future. So without further ado, let's get started with truth tables and symbols. In this section, I'm going to be talking about the 6 gates I mentioned in the beginning of this video. So AND gate, OR gate, NOT gate, NAND gate, NOR gate, and exclusive OR gate. So I'm going to start by showing you the truth table, and then showing you how to draw the symbol, and finally how to write the output if you're going to use it in an equation. So let's start with the AND gate. So this is the truth table for the AND gate. The AND gate takes 2 inputs and outputs only 1 output. If the 2 inputs are zeros, the output is 0. If one of the inputs are 0 and the other one is 1, the output is also 0. But when the 2 inputs are 1s, that's when the output is 1. So the output is 1 only when both inputs are 1 for the AND gate. Now remember what we said about zeros and ones? They are just symbols. So 0 here can be symbol of 0 volts, or it can be symbol for the switch being off, or basically anything that we talked about before. And 1 could be a symbol of 5 volts or 9 volts, or basically the switch being on. So let's go over to the OR gate. The OR gate also takes 2 inputs and it outputs only 1 output. When both inputs are zeros, the output is 0. When one of the inputs are 0 and the other one is 1, it outputs 1. And when both inputs are 1s, it outputs 1. So the output is 0 only when both inputs are 0, and that's for the OR gate. Which means that there is no option that you get output of 0 except when both inputs are 0. So let's take a look at these symbols for the AND and the OR gates. So as you can see, the AND gate has more curves and more curvy over here and here. And it takes 2 inputs, as we said, and the output is 1 output, and that's how it's written. So it's written AB or XY. Some people write it as A.B. It's the same thing. As for the OR gate, it also takes 2 inputs, as we said, and outputs 1 output. And that's how the output is written. So A plus B or X plus Y. The plus here symbolizes OR. And as for the symbol, you can see it's more pointed than the AND gate. And the difference is clear when you put them beside each other. So the third gate I want to talk about is the NOT gate. So basically, the NOT gate takes 1 input and outputs only 1 output. And what it does is revert the input. So it takes 0, it outputs 1. It takes 1, it outputs 0. So that's all what it does. It's a pretty simple gate. And that's how we draw the symbol for it. So a triangle and then a little circle after. And actually this circle is used in other gates, and we're going to see this in a second. The output is usually written in 2 ways. It's either A and then apostrophe or A bar. So next we have the NAND and the NOR gates. So the NAND gate is nothing more than NOT AND. So if you remember the functionalities of NOT and AND gates that we just did, here's what you're gonna do. You're gonna take the two inputs and then AND them, and then you're gonna take the output from the AND and then revert them. So here we have 0, 0 and 0, 1, 1, 0, 1, 1. So if you remember from the AND gate, the output was 0, 0, 0, 1. So what you're gonna do now is revert this output of the AND. So take this output and then revert it. So, and try to think what the output is gonna be only when both inputs are what. So try to pause this video and complete the table and then come back to compare your solutions with my solution in the next slide. While we are still on the subject, let me tell you what NOR is. So NOR is not OR, and it's so similar to NAND. It takes two inputs and outputs only one output. And how you get this output is by getting the output of the original OR gate and then reverting it. So if you remember, the output of OR was 0, 1, 1, 1. So what you're gonna do is gonna take this output and then revert it. Also try to find a corresponding sentence to NOR. Now pause the video and try to solve this table and then come compare your answers to my next slide. Okay, so let's see what we have here. So what we did for the NAND is that we took the output of the AND gate and then reverted it. So if you remember, the output of the AND was 0, 0, 0, 1. So what we did here is revert it, so it became 1, 1, 1, 0. And the corresponding sentence for NAND is that the output is 0 only when both inputs are 1, as you can see here. As for the NOR, we did the same thing. So we took the output of the OR, which was 0, 1, 1, 1, and we reverted it. So it became 1, 0, 0, 0. And the corresponding sentence for NOR is that the output is 1 only when both inputs are 0, as you can see here. Okay, so let's go to the symbols. So here we have the symbols for NAND and NOR. So this one corresponds to NAND. So we have the AND gate first, and then what happens is that we take the output of the AND gate and then put it into a NOT gate. So this gives us the output of the NAND, and these two gates are basically the components of the NAND gate. The output of the NAND gate is written this way. So A dot B or AB bar. The bar here is corresponding to the not AND. And this is how we draw the symbol for the NAND gate. So it's and then there's this circle we talked about a couple minutes ago, which corresponds to the NOT. As for the NOR gate, this is how it is composed. So it is composed of the OR gate, and then we take the output of the OR and inputs it into a NOT gate. So the output is in, and then it outputs the output of the NOR. These two components make this symbol for the NOR, which is OR and then the little circle we just talked about, and the output is written in this way. So A plus B bar. So next we have the last gate I'm going to talk about in this video, which is exclusive OR. So what the exclusive OR does is that it outputs 1 only when the number of 1s in the input is odd. So if we see here, when the inputs are 0, 1 or 1, 0, the output is 1. And that's the only cases that the XOR can output 1s. However, if you see here, when it's 0, 0, 1, 1, the output is 0 because the number of 1s are even. Let's look at the symbol for the XOR. So the XOR takes two inputs, outputs one output. The symbol itself looks like the OR, so it actually consists of OR and then this little curve over here. And this is how the output is written. So your first input and then plus inside a circle and then your second input. Okay, so next we're going to talk about circuits. A circuit is a path that is composed of individual electronic components such as gates and resistors, and they are connected by conducting wires in which electricity can flow. This definition is according to Wikipedia. I'm pretty sure that it's hard to understand, so let's look at a couple examples that I think you will understand and relate to. So the first example here, we have the circuit corresponding to how the AND gate works. Its components are a battery and two switches A and B and a lamp. So, and we have here the truth table, the AND gate truth table, if you remember from earlier. One thing I want to remind you of is that 0 here symbolizes that the switch is off or it is open, and 1 symbolizes that the switch is on or it is closed. So what we want to do is conduct electricity to light up this lamp. So let's see here if we have 0, 0. This means that the switches are open, so this means that the lamp is not going to light up. The second case we have here is when A is 0 and B is 1. This means that B is going to be closed, but A is still going to be open, so the current is not going to reach the lamp as well. Third case is the same thing, and finally the fourth case is when the current is going to reach the lamp and it's going to light up. Okay, so next we have the OR gate circuit. So here we have a battery, and we have a lamp and 2 switches, and here we have the truth table of the OR gate. So when both of them are 0, no electric current gonna go to the lamp, but when A is 0 and B is 1, so the current is gonna go to A, it's not gonna pass, but when it checks B, it's gonna find that it's closed. So it's gonna go this way through B and then to the lamp, which is gonna light it up. In the second case, it's the same thing. It's gonna go through A instead and light up the lamp. And of course, when both of them are 1s, the current can go through any of the 2 switches, A or B, and it's going to light up the lamp. After seeing all these things, you might be wondering, what are circuits and gates in real life? Let me show you. So what I have here is something that is called a breadboard, and it helps me build my circuit. So I have a battery that is 9 volts, and this is my source of electricity, and here I have 2 circuits. So this is a circuit and this is a circuit. Let me try it and try to guess which one is which. So I tried this switch is not working, this switch is not working, but when I press both of them, the lamp lights up. Let me try the second one. When I press this one, it's working. When I press this one, it's working. And when I press both, it is working. So this means that this part is the AND circuit and this part is the OR circuit. So let's look at the AND. According to the truth table, when both are 0, the output is 0. When one of the inputs is 0 and the other one is 1, the output is still going to be 0. But in case both inputs are 0, the output is going to be 1, so the lamp is going to light up. You can apply the same thing with the OR circuit here. So if one switch is on, this means that the output is going to be 1 and the lamp is going to light up. And when both switches are on, this means that the lamp is going to light up as well. But wait, does this mean that our computers and devices have all these wires and gates and circuits inside of them? Well, yes and no. There is something that is called ICs or integrated circuits, and that's what our devices have inside of them. Here's an example of an IC. This IC has 4 AND gates inside of it. I wanted to show you the difference in size between this IC and the circuit of the AND gate I just showed you a couple minutes ago. So you can imagine the amount of space that these ICs save. And of course, the smaller the IC is, the better. There are tons and tons of ICs and chips out there, and if I start to talk about them, I'm not gonna end this video. So I'm just gonna stop here. Thank you so much for watching. If you have any questions, please feel free to contact me or anyone from the tutoring center.